All right, so get this. We're diving into something that's like surprisingly everywhere.
It really is. We're talking about how things spread and move and change.
What kind of things?
I mean, everything from like pollutants in the air to, chemicals reacting.
Oh, wow.
Even populations of animals.
Oh, okay.
All sorts of fascinating stuff. And the crazy part is
Yeah.
we can describe this whole complex dance using like one equation.
Whoa. Hold on. You're saying there's one equation that can explain like all of that?
It's true, and it's a pretty elegant one, too.
Okay, I am intrigued. I'll admit, though, equations aren't usually my thing.
I hear you, haha, but trust me, this one is worth exploring.
Okay.
It's called the Diffusion-Advection-Reaction Equation.
Okay.
And while the name might sound a little intimidating,
Yeah.
the idea behind it is surprisingly intuitive.
All right, I'm ready. Let's break it down. Where do we even begin with something called the Diffusion-Advection-Reaction Equation?
Well, think about it this way. Imagine you're trying to, scent a room with air freshener.
Okay.
You spray it in one corner, but it takes, forever for the scent to reach the other side.
Yeah, that's true.
That's diffusion in action, the natural tendency of particles to spread from areas of high concentration to low concentration.
So that's why my whole apartment doesn't instantly smell like lavender when I just do a little spritz in the kitchen.
Exactly. It's also why a drop of food coloring slowly disperses in a glass of water.
Oh, okay.
And this concept, it isn't just about smells or colors. It plays a crucial role in understanding how heat spreads.
Right.
How pollutants disperse in the environment.
Yeah.
And even how molecules move within our own bodies.
Oh, that's actually pretty cool. It's like this invisible force constantly working to even things out.
Yeah.
But what about when there's something actively pushing or pulling those particles?
That's where advection comes in.
Okay.
Think about a kayak race on a river.
Kayaks? Okay.
Are the kayakers just drifting, or is there something influencing their movement?
What they're definitely paddling, but I mean, the current also plays a huge role, right?
Yeah.
They're being carried along by the flow of the river.
Exactly. Advection is all about the transport of particles due to the flow of a fluid,
Right.
whether it's water,
Uh-huh.
air,
Right.
or even something like traffic flow.
Interesting.
So those kayakers are experiencing both advection from the river current
Right.
and diffusion as they navigate around each other.
Okay, so we've got diffusion, which is about things spreading out naturally.
Right.
And advection, which is like hitching a ride on a current.
Exactly.
What's the reaction part all about?
All right, so imagine baking a cake.
Okay, I love cake.
You combine ingredients, flour,
Yeah.
sugar, eggs,
Yeah.
but it's the baking process, the reaction that transforms them into something entirely new and delicious.
So the reaction term is like the magic ingredient that creates a transformation.
Precisely. It accounts for any creation, transformation, or decay happening within the system.
Oh.
And just like cake recipes, these reactions can be simple or incredibly complex.
Yeah.
This is where the equation really shines, because it can capture both the movement of particles, A and D, how those particles are changing and interacting within a system.
Now I'm starting to see how this equation could be a powerful tool. It's not just about movement, it's about understanding how things change over time.
Right. And by adjusting the parameters of this equation, we can actually model a vast range of phenomena across different fields.
Okay, now I'm really hooked. Let's dive into some specific examples to see how this equation plays out in the real world.
Let's start with something simple. Heat spreading through a metal rod.
Oh, okay.
If you heat one end, how do you think the heat travels to the other side?
It's not like little workers carrying buckets of heat down the rod.
No.
It has to be spreading on its own right.
Exactly. It's pure diffusion.
Okay.
The hotter molecules at the heated end, they're vibrating faster, bumping into their cooler neighbors and transferring some of that energy.
All right.
This chain reaction continues gradually spreading the heat throughout the entire rod.
So it's like a domino effect, but with energy instead of dominoes.
That's a great way to visualize it. Now imagine you're trying to track a patch of pollution spreading in a river.
Oh, okay.
It's not just diffusing outward, it's also being carried downstream by the current.
So that's where advection comes into play.
Right.
It's adding another layer of movement on top of the diffusion.
Precisely. And this combination of diffusion and advection, it's crucial for understanding how pollutants disperse in the environment.
Right.
It helps scientists predict where pollution will travel, which informs cleanup efforts and helps protect ecosystems.
This is making me think about how weather patterns work.
Yeah.
It can't just be diffusion spreading heat and moisture around, right?
Right.
There have to be currents involved.
You're spot on. The
Yeah.
movement of air masses is a prime example of advection, and it's a key factor in weather prediction.
Okay.
But things get even more interesting when we bring in the reaction term.
Okay, so let's crank up the complexity.
Right.
Give me an example where all three pieces of the equation are at work.
Let's consider the spread of a disease. You have people moving around potentially spreading the disease.
Yeah.
That's diffusion and advection.
Right.
But you also have the disease itself replicating and potentially mutating within individuals and across a population.
Oh, wow.
That's the reaction term in action, and it adds a whole other dimension of complexity.
So it's like trying to track a moving target that's also changing shape as it moves.
Exactly.
No wonder epidemiologists have a tough job.
Absolutely. But the power of this equation lies in its ability to capture all of these dynamic processes simultaneously.
Yeah.
By adjusting the terms and parameters, we can model scenarios like how a disease might spread under different conditions.
Right.
Or the effectiveness of various interventions.
That's incredible. I'm starting to grasp the sheer scope of this equation. It's not just about understanding what is happening, it's about predicting what might happen in the future.
Exactly. And that predictive power makes it an invaluable tool in fields like environmental science,
Yeah.
medicine engineering, and even finance.
Okay, my mind is officially blown.
Yeah.
This one equation is like a universal key unlocking secrets across so many different areas of study.
It's true. And while it might seem like an abstract mathematical concept, it's rooted in a deep understanding of how our world works.
I'm curious though, are there any limitations to this equation? I mean, can it really model everything?
That's a great question. Like any model, the diffusion-advection-reaction equation is a simplification of reality.
Okay.
It works incredibly well for a wide range of phenomena, but it does have its limitations.
So it's like a really detailed map. It can guide us, but it's not an exact replica of the terrain.
Yeah.
What are some things we need to be mindful of?
One key assumption is that the medium through which things are moving is uniform.
Okay.
In reality, that's often not the case.
Right.
Think of the ocean, for example, with its varying temperatures, salinity, and currents.
Yeah.
These variations can significantly impact how things diffuse, advect, and react.
So it's like assuming a perfectly flat, smooth road, when in reality there might be hills, curves, and potholes.
Right.
We need to factor those complexities into our models.
Precisely. Another thing to keep in mind is that this equation relies on the concept of random motion for the diffusion term.
Mm-hmm.
While this generally holds true, there are cases where the movement is more directed.
Like a flock of birds migrating.
Yes.
They're not just randomly scattering.
Yes.
They have a destination in mind.
Exactly. In situations like that, where behavior or external forces play a significant role, we might need to adjust the model to accurately reflect what's happening.
So it's not just about plugging numbers into a formula. It's about understanding the nuances of the system you're trying to model and choosing the right tools for the job.
Absolutely. And that's what makes this field so fascinating. It's a constant process of discovery and refinement, always striving to create better models that capture the complexities of the real world.
This is reminding me of something you said earlier about the equation's predictive power. What are some cutting-edge ways it's being used to tackle real-world challenges?
One area that's particularly exciting is computational fluid dynamics, where this equation plays a key role in simulating the flow of fluids.
Okay.
This has incredible applications in designing more efficient aircraft, predicting weather patterns, and understanding ocean circulation.
So it's like creating a virtual wind tunnel or a digital ocean where you can test different scenarios and see how things play out.
Exactly. And the applications go far beyond engineering. In the medical field, this equation is being used to model the spread of diseases, design more effective drug delivery systems, and even understand how cells interact within our bodies.
Wow, it seems like this equation is like everywhere.
It really is. It kind of speaks to the underlying connectedness of our world.
Yeah.
You know, whether we're talking about physical phenomena like fluid dynamics or biological processes like disease transmission, there are like fundamental principles at play that we can describe mathematically.
And understanding those principles allows us to not just describe what's happening, but also to like predict and maybe even influence what might happen in the future.
Exactly. It empowers us to make informed decisions about the challenges we face, whether it's protecting our environment, developing new technologies, or improving human health.
I'm also thinking about how this equation could be used in fields like economics or social sciences.
No, yeah.
Could we model things like the spread of information or the dynamics of social networks using these principles.
That's a fascinating area of exploration, and researchers are already delving into those applications. The diffusion of ideas,
Yeah,
the flow of capital,
right.
the formation of social groups, these all involve movement, interaction, and transformation
Yeah.
concepts that our equation is perfectly suited to address.
It's mind-boggling to think about the potential. This one equation is like a lens through which we can view and analyze
Yeah,
so many aspects of our world.
it's true. And as we continue to develop new computational methods and gather more data, the applications of the diffusion-advection-reaction equation are only going to expand further.
I have to admit, I came into this conversation a bit skeptical about the relevance of an equation to my everyday life. But I'm leaving with a whole new appreciation for the power of mathematical modeling and the interconnectedness of seemingly totally different fields.
I'm glad to hear that. It's all too easy to compartmentalize knowledge, but in reality, everything is connected. And it's through exploring those connections that we make the most fascinating discovery.
Well said. And I hope our listeners are feeling just as inspired to look at the world with a fresh perspective, noticing the diffusion, advection, and reaction happening all around them.
It's been a pleasure diving into this topic with you and our listeners. Remember, curiosity is the fuel for discovery. So keep exploring, keep asking questions, and never stop learning.
And on that note, we'll wrap up this deep dive into the captivating world of the diffusion-advection-reaction equation. Until next time, keep those brains buzzing.